Okay, so we showed how we could start with a signal at a fine scale, break it up into a sequence of signals at increasingly coarser scales in both the wavelet and the scaling domains, and represent those as just the wavelet coefficients and scaling coefficients. And then we can go, using those coefficients, we can get back to the coefficients, the scaling coefficients at our finest resolution, which is equivalent in this case to a signal x of n we're talking about. So that worked for HAR wavelets, and we kind of went through the math, and it just came out nicely. But we've already and also looked at other wavelets, scaling functions, such as the Darwishi scaling function, that don't look anything like the HAR functions, which were just, well, they look like that. So our scaling spaces. So here, for example, we have the HAR scaling function. So what about these fancier wavelet functions? Can we come up with some sort of a reconstruction for those? Those look kind of useful. So we would like x tilde to be exactly equal to xn. Now, often we relax the concept, and that we call that perfect reconstruction. But we often relax our notion of perfect reconstruction to allow some delay, because we would like our filters to all be causal. So if we have the filters H0, they're going to introduce a little bit of delay into the signal just because of the nature of a causal filter. And so we will require x tilde of n equal x n minus m for some delay m, and that's generally okay. If that's not okay, and there has to be no delay, then it must be assumed that you have non-causal filters available for use, in which case you could just put a delay of z to the m out front, and that would get rid of it, and away we go. But assuming we don't have these physically unrealizable things, let's just go ahead and use this. So we need to do some general analysis, and this makes more sense in the context of the Z transform that we introduced in the last lecture. And so we have Sj minus 1, the scaling function, coefficients at, and their Z transform is scaled j minus 1. We have that that's equal to 1/2 H0 z to the 1/2 x z to the 1/2 plus H0 negative z to the 1/2 and x, whoops, there's no naught there, just x negative z to the 1/2. So we took advantage of the fact that this point right here is the Z transform is x of z H0 of z, and then we did the downsampling and using the relationships that we developed previously, and that's what we get. So u of z is now that same thing upsampled and then filtered by g of z. Well, fortunately, G of Z doesn't undergo any particular weird process like upsampling or downsampling, so it just comes out front. Now, where before we had Z to the 1/2, remember when we upsample, we just get Z squared, so this is going to be H0 of Z, X of Z, plus H0 negative Z, X of negative Z. And we get something almost identical for the wavelets, with just a little bit of sign differences as before, and it's using filter 1 instead of H0. So H1 minus C X minus C. So H will have those signs differences in it, at least they did for the Haar wavelet, and we'll assume that that general idea is going to hold. So now we get to a really ugly expression, and that is that X tilde of Z is equal to 1/2. We're going to try to factor out our X of Z and X of minus Z, and it should become clear really soon. H0 of Z plus G1 of Z, H1 of Z, all times X of Z plus 1/2. And here we have these other funny terms, H0 of minus Z, so that was one of our aliasing terms, and G1 of Z, H1 of minus Z, so it's going to give us another aliasing term, X of minus Z. And we want this to be equal to Z to the minus M X of Z. So this boils down to two conditions. That is that this expression here has to equal 0. So I guess we don't care about the 1/2. So this is aliasing cancellation, alias cancellation, and then the other condition is that, whoops, this first term, the filter terms, need to equal 2 because of that 1/2 in there, times C to negative M. And so this means this part ensures that there's no distortion, only a delay applied to X of Z. So how do we design filters like this? So what conditions could we do? One thing we can do, and I might say that there are scores of papers, hundreds of papers, proposing different ways of coming up with G and H. Some of them are pretty dense, difficult to understand. There's one particular group of researchers who I respect the professor a lot. He's a great guy, very nice, wonderful. But they had a paper or two every month in the IEEE Transactions on Signal Processing as they came up with different ways of designing these filters. So we're not going to go into all the ways of coming up with designs, but we'll come up with the conditions that they're going to meet and discuss that a little bit. So one thing we can do is suppose we already have our G's, just for now. Then a natural choice for our H's is H1, or let's start with H naught of Z is equal to G1 of negative Z, and H1 of Z is equal to negative G naught of negative Z. Okay, so this isn't going to solve everything, but with respect to our aliasing cancellation, let's see what happens there. This is going to be, we'd have G naught of Z. So I'm going to number these. Times G1 of negative Z. Oops. We have H naught of negative Z already, so that would be G1 of Z. And then we'll have G1 of Z. And H1 is going to be negative G naught, so we have the negative out there. And the two negatives on the Z cancel. And there we go. And that equals 0. So beautiful. No aliasing, or at least alias canceled. Hang it up. We can go home. So once we've done that, then all we have to do is design the G's so that we have the no distortion requirement met. But let's just look at a quick example here, and just to kind of, well, actually we're about out of room here, and there's one just example of how this might look, but let in the notes. So maybe I'll quit right now. So basically what we would have is H of Z, or G of Z is maybe polynomial in Z, some FIR filter, and H of Z is going to be polynomials with the same coefficients but some sign changes, and the filters are going to be swapped. So here, this next one, we define T of Z is now going to be equal to G of Z, G1 of minus Z, minus G1 of Z, G naught minus Z, and we need to have that equal to the Z, or Z to the negative M. So How do we do this? Generally, we usually fix G naught, and then find G1. And we'll use some optimization method to do so. So back to the Dervishes wavelets. That's what this is all about. We can choose some wavelet functions and optimize, and we get this set. The Dervishes wavelets have certain criteria that were used in the optimization to come up with these wavelet coefficients. And it was, like I say, it's not a trivial way to go, but these are the basic concepts of filter bank design. And with the correct choice of G, you can have maybe the frequency response that you like. I will say that one of the ways that the Gs are often designed is based on some transform, like the cosine transform, to make it easier to both compute and to come up with coefficients that have properties that are kind of easily comprehended and understood. So, perfect reconstruction filter banks. It's a deep rabbit hole, but those are the basic concepts.